Now, we talked earlier about a random variable is a variable whose value is a numerical outcome of a random phenomenon. We often denote random variables with a capital alphabetic symbol like X, Y, or as whatever. It could be just a capital letter. And a normal random variable we're going to denote here as X, and you'll see that squiggle mark saying that X is approximately normally distributed. That's what the N stands for, and in parentheses it's going to be the mean and the standard deviation. The probability distribution of a random variable X tells us what values X can take on and how to assign probabilities to those values. Now, random variables can take on can be two different types. One's a discrete random variable, one's continuous. Now, the possible outcomes when they're discrete, that's when we have a discrete random variable, and when the values of our random variable take on continuous values, we call that a continuous random variable. So in other words, if the random variable can only take on values in an interval with probabilities given as areas underneath the density curve, we say that the random variable is continuous. So let's look at some discrete random variables. They're designed to model discrete variables, obviously, and often they're counts of things. So if we said our random variable is the number of pets owned, or our random variable is the numerical day of the month. Another example would be a random variable being how many days of class missed. A continuous random variable is designed to model continuous variables, and they're usually measurements of. So examples would be my random variable could be the weight of something, or the temperature at a certain time of the year, or in a certain place. Or it could also be my random variable could be the time it takes to travel to work. We're going to look first at the discrete probability model. Now, the discrete probability model is the model of a discrete random variable. So it's going to relate those values of our random variable with their corresponding probabilities. And we generally can see these in a table or a graph, and sometimes in the form of a mathematical formula. So let's look at a discrete random variable. We would write the probability that our variable equals a particular value as we see here in red. Now remember, with the discrete model, the probability at a particular value can have an actual value. But remember, in the continuous model, the probability at any particular point is always 0. So, back to the discrete probability model. Let's look at some examples. If you let X be the number of heads when we toss a coin, there are two possible answers. You could see a head 0 times, or you could see it 1. So the probability that my random variable equals 0, so I see 0 heads, I have a 1 out of 2 chance of that happening, or 0.5. And the probability of seeing 1 head is, again, 1 out of 2, or I have the probability of seeing 1 head as 0.5. Let's look at rolling 1 die. If X is the number rolled, then the probability that X equal 1 is 1 out of 6. The probability, let's say my random variable X is the number rolled, so I would say the probability that X equal 2, to roll a 2, it's also 1 in 6, and I could use that for each possible roll. So let's look at some properties that have to be met in order for a model or a distribution to be a discrete probability distribution. The first thing is that all the values, here, let me change them. Let's look at these properties that have to happen. The probability of any particular value has to be a number that's a probability. It has to take on values between 0 and 1, including in 0 and 1. So it can't be any number greater than 1, and it can't be any negative number. Those would not be probabilities. So probabilities only take on values between 0 and 1, including 0 and 1. So again, if you should get a probability and you calculated it and you got 1.2, you would know you did something wrong. Now, the second rule says that if I take the whole space, all the possible values my random variable can take, and add up the probability of each of them occurring, it should equal 1. So remember that sign there is the summation sign. So let's look at this distribution right here and see if it truly is a discrete probability model or a probability distribution. Well, first of all, looking at the second column, that's the column of probabilities, those numbers look right. They're all between 0 and 1, including 0 and 1, and they definitely are. They're strictly in between. Now, when I add them, 0.2 plus 0.6, that's 0.8, plus 0.1 is 0.9, plus the other 0.1, that gives me 1. So this truly is a discrete probability distribution, and I could ask all kinds of questions. I could say, what's the probability that x equal 2? And you would say, oh, it's 0.6. What's the probability that x is 5 or 6? Because these are disjoint, I just add those probabilities, so the probability of 5 or 6 equals 0.2. I could also ask, what's the probability that x is less than 4? Well, because we don't have probability at 4 and 3, the probability of those are 0, it only matters of 2 and 1. So the probability that x is less than 4 is just the same thing as the probability that x equals 2 plus the probability that x equals 1. So it equals 0.8. Now what if I ask what's the probability that x is greater than 7? Well, there is no probability greater than 7, so that equals 0. The only values that x can take on is 1, 2, 5, or 6. Now look at this distribution. Is this a probability distribution? Right away we see that one of the probabilities is negative, so it is not a distribution.